Hello all, my name is Mr. Adams and this is a video on buffer calculations, okay? In a previous video, I go over the theory of buffers, so please refer to that. In that video, I'm going to ask you guys to review your conjugate acid-base pairs in Bronsted-Lowry theory. I'm going to ask you to review the K expressions, okay, in terms of equilibrium constants, and also to review Le Chatelier's principle. So please look at that video. And this video is primarily working on calculations. Before we jump into calculations, I do want you to check out my site on YouTube. Okay, it's called Basic Chemistry for Pre-Nursing and Regents. Please like and subscribe. It's all free. And also, if you have anyone trying to get into nursing school or having issues in nursing in terms of NCLEX or whatever, they can check this site out. It's called adamsnursingreviews.com. And it has it's a one-stop shop for everything that you need in terms of nursing. Okay, now typically, guys, you're given a chart like this in lab, okay, and you're asked to do certain calculations with buffers. So what happens if we have a weak acid, which the universal symbol for weak acid is HA, right? And you write the equilibrium expression for it, you're gonna get Ka, okay, equals to the concentration of H30 plus, okay, square brackets meaning concentration molarity, times the concentration in the A minus, okay? Now, that will be all over HA. Now, water, since it's the medium counter reaction, does not appear in the K expression. Now, what happens next? We take some logs of both sides, we do some simple rearrangement, and then we wind up with this expression that the pH, okay, is equal to pKa, all right, plus log of A minus concentration over the HA concentration, all right? Now, this is very important because this ratio, right, over here, depending on how much is affected, affects how much the pH is affected. So if this ratio over here is not affected much, okay, this pH value will go unchanged. And this is essentially what you want in a buffer. Because remember, buffers are solutions where if you add or change the H30 plus or OH minus concentration in terms of acid or base, the overall pH value will not change that much, okay? So let's do a simple problem. Number one, what is the pH of a buffer containing equal concentration of H2CO3 and HCO3 minus, okay? Now simply we set up our Henderson-Hasselbalch equation, which is pH equals to pKa plus log, okay, of the HCO3 minus concentration, because that's your A minus, that's your conjugate base, over H2CO3. Okay? Now, if these concentrations, right, the HCO3 minus and the H2CO3, right, equal, right, you will essentially, right, get the log of 1. Okay? And from math experience, okay, the log of 1 always equals to 0. So what this problem is showing is that anytime you have equal concentrations of the acid and the conjugate base, okay, the pH will be equal to the pKa, okay? And you don't panic. You look on your chart for the pKa value for H2CO3 and you find it and you write it down. And in this case, the H2CO3 value, if I'm not mistaken, will be 6.374 carbonic acid. Now, there's one thing I didn't explain. These guys right here, right? These are the names of the acid. These are the actual formulas of the acids, right? Now remember, acids are the guys that release or give off or donate their H plus, okay? So if you want to find the conjugate base of any of these guys in this list right here, you simply take away H plus from it, and that will be your conjugate base. These values here are called the Ka values, or the ionization constant for the acids. They're telling you to how much extent will these acids donate or release their protons. Now this -13 is a very low number, right? So this hydrogen phosphate ion will not release a large amount of H plus compared to something like the phosphoric acid, which is only 10 to the -3. Okay, so once again, these values of Ka tell you to what extent H plus is released. And these values here, they're called the pKa values, right? And they're obtained by taking the log, okay, of the Ka values. Alrighty. Okay, so let's look at example 2. It says to determine the pH, right, of a buffer solution if the NH4 ammonium concentration is 2 times that of the NH3 concentration. Okay, so we know from experience, right, that our formula is pH equals to pKa plus, okay, log of the A minus concentration over the acid concentration. Okay? Now, in this case right here, we are looking for the pH. We don't know what it is. Now, the pKa for ammonium, right? You don't panic. You look at the table. Now, ammonium ion is over here, NH4 plus, right? And the pKa value is there. So that's what, 9.25. Okay, so we're going to substitute that here, 9.25, right? And that's going to be plus log. Now, the situation is that we have NH4 plus, okay, twice the concentration of the NH3. Now we know NH4 plus, since it has one more H plus than NH3, the NH4 plus will be our acid, right? Okay, so we'll put him in the bottom. So he's twice the concentration of NH3, which goes in the top, and NH3 is our A minus, all right? So in essence, what we're doing now, we're taking a log of 0.5, okay? All right, so let's see how that goes. Okay, so we're going to have pH equals to 9.25 plus the log of 0.5, which I'll calculate right now. All right, we have log, we have 0.5, okay, and if I'm not mistaken, that is -0.30. Okay, so plus -0.3, okay, and -0.3, right, plus 9.25 is around 8.95. Okay, guys, moving right along to example 3. What would be the pH of a buffer solution? It has phosphoric acid, H3PO4, and the concentration of the H3PO4 is 0.36. It also has the conjugate base of the H3PO4, which is H2PO4 minus, and that concentration is 0.3. Now, if you notice, right, the concentrations are not equal, so they won't go to 0 in terms of the log, okay? So the pH will not be equal to the pKa. But if you look carefully, right, and if you know that this guy right here is your acid, right, okay, you can make a prediction, right, that since the acid has a higher concentration than the conjugate base, that the pH eventually will be a little lower than the original amount. Okay, so let's check it out. So let's write the Henderson-Hasselbalch equation again, which is pH, okay, equals to pKa, okay, plus log of A minus concentration over HA. Okay. Alrighty. Now what we're going to do, we're going to do some plugging in. We are looking for pH, right? So we don't know that guy. Alrighty. Now the pKa for H3PO4 can be found on our table over here, right? This phosphoric acid at the top. Okay, and that value is 2.1. Okay, so we plugged it in. So pKa value is 2.1. Alrighty. Now we put plus. Okay, now the log of the A minus in this case is 0.3. All right, so it's log. All right, A minus concentration is 0.3. Okay, and the HA concentration, as we said before right here, is 0.36. Okay, so what we're going to do, we're going to divide those two guys. Alrighty. Okay, and then take the log of it. All right, so we'll do that right now. Okay, log of 0.30 divided by 0.36, okay, gives me approximately 0.08, okay, negative 0.08. So pH, alrighty, will be equal to 2.1 plus negative 0.08. Okay, and when we add those guys up, we will approximately get, all right, 2 plus 2.1 equals to pH equal to 2.02. So your prediction was correct. Okay, so you have a little more acid in this case right here. It will lower your overall pH value. But as you notice, right, in terms of the pKa and PA, the pKa and the pH, right, they're not equal. All right, no problem. Alrighty. Okay, guys, let's look at example 4. What would be the final pH of the buffer solution in example 3 if 0.04 moles of sodium hydroxide NaOH is added to 0.40 liters of this solution? Now, it seems complex, but the thing is, what you have to do, you have to take it bit by bit by bit. Now, there's a couple of things that you have to consider. We're considering example 3, right? So let's go back to example 3. And we made a successful buffer because this is our acid and that was our conjugate base, right? And we figured out the pH of this buffer. We figured out that the pH is 2.02, right? Okay, now you have to use some logic. If you're adding a strong base, sodium hydroxide, right, to a solution, right, what would you expect the pH to do? You would expect the pH to go up, right? Now, the thing is, if it was pure water, the pH will go up drastically to a very high value, like 12, pH 12 or pH 13, right? But since we have a buffer on our hands, we are not expecting the pH to go up that much. Okay, so next thing you want to do is look at the situation. You're given 0.04 moles, right? Okay, I'm going to put MOLS for short there. And we're going to divide that by, okay, the volume here, which is 0.4 liters. Now, what are we trying to find? We're trying to find the concentration of the OH minus, right? So when we divide these two guys right here, that will give us 0.01 big M. And that's important to us. All right, so that 0.01 big M, we're going to use that in a second. Now, what we say to ourselves, what are we starting out with? So let's look back at our chart right here. We are starting out with, okay, 0.36 big M of H3PO4. So let's put that in our chart, all right? So H3PO4, we're starting out with 0.36 big M of it, okay? We're starting out with 0.01 big M of the hydroxide solution, right? Now, we're also starting out, if we look back at question example 3, 0.30 big M of the conjugate base, which is H2PO4 minus, right? So we're going to put that value over here, 0.30 big M. Now, why do we need these values? What's going to happen is when we add the base, right, the OH minus, that's a stress, okay? Now, the reaction will shift to relieve that stress. So this reaction will shift to the right, okay? It's going to produce more H2PO4 and try to get rid of this base. So this base will be used up, okay? All right, do subtraction there. It'll be all used up, and it will react with some of the H3PO4. Now, what we're going to do, we're going to take away 0.01 big M from the 0.36. Why is that? Because the OH minus, right, is reacting, the OH minus is reacting with the H3PO4. Okay, so this will reduce now to 0.35 big M. Alrighty. Okay. And that's nothing. Okay. Now over here, we're going to produce more H2PO4 minus, right? Now, how much more are we going to produce? Since the mole ratios and the equivalency, we will produce 0.01 more of H2PO4 minus, and that's going to give us 0.31 big M. So now, what do we have? We have our HA value now as 0.35. We have our A minus value as 0.31. Now what we're going to do, we're going to use these guys in the Henderson-Hasselbalch equation, right, to figure out what's the final pH going to be. So let's see what happens. So we're going to have pH, alrighty, will be equal to the pKa. Now let's check what the pKa value is. It's 2.1. We have it here already, so let's use that. 2.1, all right, plus log of the A minus value. The A minus value is here, which is 0.31. So 0.31 goes on the top. Okay. Over the concentration of the acid, which is HA, which is 0.35, H3PO4. So then 0.35 goes in the bottom. Okay, we're almost there. Now what you do next, you do a simple calculation, all right? We have to find what's the log of 0.31 divided by 0.35. So let me do that right now. So log of 0.31 divided by 0.35. Okay, let me see. Okay. Log of 0.31 divided by 0.35. And that gives me what? 0.0527. Okay, for argument's sake, we're going to say negative 0.053. I'm going to round it a bit. Okay, no problem. And we're going to add that to what? To 2.1. So we got 2.1 plus negative 0.053. This guy right here. It's a bit muddly, but no problem. Let me put a box around it. All right. We're doing this calculation right here. Okay. So let me add that up. So, okay, 2.1. 0.1 plus 0.0 plus negative 0.053 equals, okay, for my calculation I got 2.05. all right, so 2.05, all right, by my estimation, and that answer seems reasonable. Why? Because we added, right, we added base to it, strong base to it. We expect the pH to go up, but since it's a buffer, right, okay, it's not going to go up that much drastically. So the original buffer pH was 2.02, and the final pH after we added the base was 2.05. This buffer is pretty decent. Okay, guys, this is our last question. Example number 5. You are asked in the lab to make a solution of pH 5.5. How would you go about this? Okay, we're sort of kind of experts now. We know from experience, right, that this guy right here is our acid, HA. And this, on the other side, our conjugate base is our A minus, right? Okay, now we're going to use the Henderson-Hasselbalch equation, right, to get to this pH value which we desire over here, right? So we know from experience, right, that pH is equal to pKa, right, plus log of the A minus concentration, which in this case is CH3 COO minus, okay, over the concentration of the acid, CH3 COOH. All right, so we're going to put in the square brackets to represent concentration and molarity, right? Now, here's the deal. They did not give us any values, concentration values for the HA, the conjugate base, right? So what we're going to do, we have to do some more manipulations. We know that we desire the pH of 5.50, okay, because that's given to us in the problem right here. That's the pH we want, right? We can look on the chart to figure out what's the value of pKa for acetic acid, the HA. So we're going to go back and we're going to take a peek at our chart, right? Okay, now you have this chart in your labs or in your reference table or so on in your textbooks to look at, right? So we're going to see that acetic acid is over here, okay, and that the pKa value is 4.75. So we're going to use that, right? So moving back to example 5, our 4.75 goes there, and it's going to be plus log of the CH3COO minus, right, over the CH3COOH. All right, we take a breath. Now what we're going to do, we're going to transfer this 4.75 onto the other side for like terms. So we get 5.50 minus 4.75, okay, and that's going to equal to this this over here, yeah? Okay, so 5.50 subtracted 4.75 gives us 0.8, right? Okay, and that equals to log, alrighty, of CH3COO minus concentration, okay, over CH3COOH. This is HA, all right? Okay, squeeze it in there. Now, we're almost there, folks. What we have to do now is go back to our memory banks and math, right? We have to take the anti-log of both sides to get rid of this. So when we use the anti-log button, if you forgot, is the 10 to the X button on your calculator. So you take the 10 to the X button, you plug in 0.8, okay? And what's going to happen is when you do that, right, you should get a value of 6.3, okay? So you will get 6.3 on this side right here, equaling to CH3 COO minus concentration over CH3COOH concentration. Now, what is that telling you? Simply, if you want to make a solution that's 5.5 pH, and so the pH using and as a buffer, alrighty, what you have to do, right, is have this guy right here on top in 6.3 times concentration of this guy in the bottom. So how do you do that? This guy in the bottom, for example, you have a nice number like 0.1 or so, or 0.01, and the top number, this concentration here, will be 6.3 times that amount, and you're done. All right, good. Now, guys, this is my video, okay, on calculations, of buffers. Please check out my original video on the theory. Once again, this is my site, Basic Chemistry for Pre-Nursing and Regents, on YouTube. Like and subscribe. It's all free. And please check out adamsnursingreviews.com for any of your nursing needs. Take care.